Understanding static charges was of course very interesting, but they as such are of not much use. Exciting things really happen when these charges they start moving, and that's when we come to the current electricity. So now let's understand how to get these charges actually moving. So we already understood that we can create separation of charges, so the charges can be separated. We can create positive as well as negative charges. So I have two jars here. Now somehow, right, just let's just suppose somehow I have managed to fill one of these jars with positive charges and the other one with negative charges, right? So what I did was essentially I took out electrons from this jar and I put them in the other one. Okay, so this is, let's say that this is jar 1, this is jar 2. I took out electrons from jar 1 and I pushed them into jar 2. As you can understand, initially when I am moving the first electron, it would be relatively very easy because there is no charge in jar 2. The jar 2 is completely empty. So the first electron I should be able to pry away from jar 1. I should be able to take it from jar 1 and put it in jar 2 relatively easily. The second electron, when I am trying to do that, I would require a little bit more energy. Why is that? Because jar 1 is already positively charged. There is a positive charge right there. So I have to use some energy to pry away the electron, which is negative. So positive, negative, they attract. So I have to use some energy to pry away the electron. And then when I'm trying to insert it into jar 2, I would need still more energy because the jar 2 is negative, and negative, negative, they would be repelling. So I use a little more energy to push it into jar 2. And similarly, the third electron, I would really need to pull it hard from jar 1 and push it really hard in jar 2, right? So slowly and gradually, I would be spending more and more energy as I am taking away the electrons from jar 1 and putting them into jar 2. Okay, so there is the key thing I want you to understand is that when I am doing this charge separation, I need energy. Okay, so there is a need of energy in this process. So this is the first thing that we need to understand. Now let's say that I connect my jar 2 with jar 1 using an electric wire. Okay, so this is a copper wire, normal wire that we see in our households, nothing special. I mean, the special thing about this wire is of course that it can conduct electrons. So what does it mean? That although the electrons cannot really escape, they cannot go into the air, the jar is closed, okay, we don't allow them to escape, they can and they are allowed to travel along this wire. Okay, so there is a wire connecting this negative and the positive charges in the respective jars. So there is a wire connecting that. As soon as I connect this wire, think about what would happen. I mean, think that you are an electron sitting in jar 2. What would you feel? You will feel a lot of repulsion from all the electrons around you. So you would really try to escape. So as soon as I connect this wire, the electrons start escaping from jar 2, and of course they are very happy in jar 1 because there is positive charge there, so they are attracted. So they quickly go into jar 2. Okay, so this is the reverse process. We used up energy when we were separating the charges. We would really need to put some energy, and here the electrons are now traveling on their own. Okay, so that is these electrons which are traveling on their own along the wire can be made to do work. So for example, if I were to connect a light bulb right here, okay, then this light bulb, as the electrons go through it, it will start glowing. Okay, so this is a very simple process of making these charges do some work. Traditionally what happened was the current, the electric current, okay, this flow of electrons is known as electric current. It is known as electric current. Okay, traditionally what happened was when Benjamin Franklin was doing his experiments, he just assumed that the current was due to positive charges and not really negative. Okay, so the current was not due to, in his times the electrons, they didn't really understand that. So he thought that the current was there. He saw that something was flowing, but he thought that this was positive charges. So although the electronic current, the current due to electrons, is from the negative towards the positive jar, the traditional current or the current that Benjamin Franklin thought is in opposite direction. Okay, and this is known as conventional current or just current. Okay, this is in opposite direction. It goes from the positive to negative, and in the electronic current electrons are flowing, like negative charge particles are flowing, in the conventional current, we say that positively charged particles are going. Okay, so that is the conventional current, and the bottom one is the electronic current. Okay, so this is the key thing that we need to understand. Similarly, we said that in the beginning that when we were separating the charges, we were prying away the electrons from the positive jar and moving them to the negative jar. Okay, this was the electronic way of looking at it. If you look at it conventional way, what we are actually doing, what we would be doing, we would be prying away positive charges from the negative jar, right, from this jar, and putting it into the positive jar. Okay, so we are prying away the positive charges from the negative jar and putting them into the positive jar. Okay, so here what we have done, this is the conventional way of looking at things, and this is actually what we would be using from now onwards. So think about it. Although in actual circuits electron might be flowing, but we always conventionally, when we show in the arrows, we always show the conventional current in which the positive charges are flowing, and that is always in opposite direction. So the equations and everything does not change. It is just the polarity of the charges and the direction of the arrows that changes. Okay, so that so far it is, I hope it is clear. Now our jars 1 and 2, okay, these are what we have labeled them. Okay, let's now introduce some terminology. Okay, so one thing that we introduced was the idea of conventional current. Okay, so that is the conventional current, and it flows from the positively charged jar to the negatively charged jar. Okay, so that is what the conventional current is. That's what we will draw now. And of course, we are prying away the positive particles, positive charges from this negative jar and taking them to the positive jar. Okay, when we are doing this prying away, we are using some energy, okay, to move a charge of 1 coulomb from this negative jar and putting it in the positive jar. We are doing some work. This work is known as the EMF, or electromotive force. It is something which is inside the battery. It is the work that the battery is doing to create the charge separation. Okay, it is inside the battery. This EMF is inside the battery. Is the mechanism inside the battery which is creating this charge separation. What happens as a result of this EMF? This work done by the battery is actually available at the 2 terminals of the battery. Okay, so this, our 2 jars, the top of the jars are actually 2 terminals of the battery. The 2 terminals of the battery, this work done, the EMF inside the battery is available. The work done inside the battery is available as a potential difference on the 2 terminals, and this potential difference is what drives the electrons or the current from the positive and negative end. So that work done inside the battery is available outside as potential, or the voltage of the battery, and this voltage of the battery drives the electric current and allows us to do all sorts of work. The 2 terminals of the battery, one is positive charge. Okay, so this is the voltage available right here. Okay, I'll just show it here. Voltage, and this voltage you might have seen it inside, like written on the battery, 1.5 volt, 3 volt, 9 volt. Okay, for example, here I have a 9 volt battery right here. Okay, so this is 9 volt battery, and this is the voltage available on the terminals because of the EMF, the work done inside the battery. This terminal, which is positively charged, okay, the positive terminal is known as anode of the battery, and the negative terminal is known as cathode of the battery. Okay, and when I connect the anode and the cathode, I can get electric current. Okay, and the current flows from anode to cathode. Now, of course, our jar battery, although it's very good for understanding the concepts, it is a little cumbersome. Think about carrying 2 jars and putting them inside a torch, or putting them in your cell phones. That would be very, very difficult. So to make things convenient, inside a battery we have these 2 jars. Okay, we still have these 2 jars. They are essentially two separate containers inside the battery, and there is some electrolyte, some chemical inside the battery which is doing the work of separating these charges. So anode is, of course, like we said, is the positive terminal, and the cathode is the negative terminal. The terminal with the bulge is actually positive, that is the anode. And of course there is electrolyte, there is some chemical reaction inside going on inside the battery which continuously separates the charges and makes them available at positives at cathode and negatives at anode. And this voltage is actually available outside the battery, is written in the at the top of the battery on its wrapper, where it says it's 1.5 volt or whatever. So now that we have understood one of the important parts of the electrical problem, which was the generating the potential, how to actually get the energy, the battery, let's look at the other important aspects, which is also discussed in your book, which is an electric bulb. Okay, so we need, once we have the electricity, we need to put it to good use. And the most common example is, of course, an electric bulb. So if we look at it, the detailed structure of an electric bulb, it is made up of the most important part is, of course, the filament. Right? This is the center part of the center wire inside the bulb, a very thin wire, it's a filament, and a very long one too, all coiled up inside. This is what gives the light energy. Okay, when we light the bulb, this is the part which actually generates the light. This center coil, the center filament, is connected on the two sides using wires. One of these wires goes to the very bottom of the bulb. It is known as the foot of the bulb. Okay, it is at the very bottom, the tip, bottom tip. The other wire goes, and the other side, right? The other wire goes and connects to the base of the bulb. This is where the bulb attaches the holder. Of course, the bulb is made up of glass, which we know. Inside the bulb, right, the filament glows very hot. It is very high in temperature. So at that high temperature, just to prevent the filament from reacting with the air, from oxidizing due to the oxygen, we remove all the air from inside the bulb. And instead, inside the bulb, we put an inert gas, a gas which is not so reactive. For example, argon. Argon is a good example of such a gas. So the way, right, similar to the battery, inside the bulb also, we have two terminals. Okay, the electricity or the electrons enter from one of the terminals, pass through the filament, and they go out from the other terminal. Okay, so this is very important, and this is the reason why the filament is so important. So that we can fit the very long filament inside the bulb, it is coiled up not once but twice, right? So we make a coil from the wire and then we coil that coil again. Okay, so it is double coiled. That's what we call it. And of course, as the electrons from the current, as the electrons pass through the wire, the filament exerts some pressure. It sort of does not allow the electrons to flow through smoothly, and this thing generates this friction, kind of friction inside the filament, what we call resistance. Okay, the technical term for the filament stopping the electrons is resistance. This resistance of the filament actually generates the heat energy. This heat is so large, right? This resistance is so large that the filament reaches a very high temperature. So we need to make a filament of a material which has high resistance, and at the same time it has very high melting point. And a good choice for such a material is tungsten. Okay, so tungsten is what is used to make the filament of the electric bulb. So now that we have studied the two very basic elements inside our two basic electrical components, we can put them together, right? And here is some example. Here is an example. I am putting them together right in front of you. So this is a battery. It is connected. One end of the battery is connected to one end of the bulb. The other end of the battery is connected to other end of the bulb. And as soon as I do that, the bulb lights up. Okay, it is very this thing is very entertaining. So you should definitely do this at home. You can try it, okay, by using a battery to light a bulb. And if you notice, the only correct way to connect a bulb to a battery is if I connect one end of the bulb to one terminal of the battery, and the other end or the other terminal of the bulb is connected to the other terminal of the battery. There is no other way to make a good connection. And of course, at the same time, we also have to make sure that all our wires are properly connected. There is no loose connection, nothing like that. And as soon as we do that, the current flows, the battery drives the electrons. Okay, this is what driving force. It drives the electrons through the wires, through the filament of the bulb and back. And of course, the bulb lights up. One more element which is important inside our okay, this connection, the way we connected it is known as a circuit. Okay, as soon as the circuit is complete, the electrons flow. If the circuit is incomplete, it is broken, the electrons don't flow. Okay, so this is a closed circuit when it is complete, and it is an open circuit when it is not complete. Okay, and the closed path, right, along which the electrons would flow through the wires, through the battery, through the bulb is known as a circuit. One of the other important elements inside our electrical circuit is a switch. Okay, notice I have created a kind of a switch here, which is a very manual. It's a very kludgy switch, if you will, wherein I make a connection here, then the circuit is complete. If I disconnect, then the circuit is incomplete. Little more sophisticated switches are available in our household. They are available in batteries. Okay, that's when we use it. And one such circuit is given in your book also. One such switch is also given in your book, where they use a safety pin to make the connection or break the connection. So the safety pin is makes the connection, then the current flows through the safety pin and the bulb lights up. If the safety pin is turned on one side, then the connection is broken, and of course the bulb does not light anymore because there is no path for the electrons to flow. The circuit is broken. Now we have understood this concept already. Okay, this as we were going through the circuit, we have understood the concept of electrical potential. But just let's revisit it. As we saw in our jar battery, we had created a mechanism for moving the charges from one side of the battery to another. So that's what we had done. And as we were moving the positive charge from the cathode towards the anode, we called that we had to do some work, and we call this work EMF, or electromotive force. That's what we called it. Now the same electromotive force is available in the circuit, right? When the battery is connected to the circuit across the two terminals of the battery, the same electromotive force is available externally as a voltage. So this is the voltage which is written on the battery as 1.5 volt. This is an example of a 9 volt battery. The EMF inside the battery gives rise to the voltage or potential difference outside the battery, which drives the electric current in the circuit. This is very similar to the potential that you would get, potential energy that you get when you climb up the hill, right? During your climb uphill, you are spending the extra energy to gain, and this energy is converted to potential energy. Okay, this extra work done that you are doing climbing up the hill, the extra energy that you are putting in doing the work gets converted to electrical energy. On your ride downhill, you don't have to put so much effort because now you can use the extra potential energy that you already have. So similarly, in the battery also, the energy given by the battery is we can use it to drive and do work around in the electrical circuit. Now, of course, the voltage available outside the battery and the EMF, they are measured in a unit called volts. It has been given after an Italian scientist, Alessandro Volta. Okay, and he was actually the inventor of batteries, and that's why we have given him credit and given the units of the potential as volts. Now the next important thing inside the electrical circuit is, of course, the flow of current, right? The flow of electrons. The flow of electrons across any cross section of the electrical circuit is known as electric current, the rate of flow. Okay. Electric current is measured in units called ampere, and they are actually base SI units. If you have studied from our past lectures, they are base SI units, and they have been named after a French scientist, André Marie Ampere, who actually was a very talented scientist. He inventor actually. He invented a number of things, and he improved upon things like, for example, electrical telegraph. So of course he was important. And that's why we have a unit named after him. The next important concept is the concept of electrical resistance. Okay, like I told you, all the material that we see around us, okay, all the normal day material, normal wires and switches and all of those things, as the electrical current flows through them, they offer some resistance to the flow of this electric current. They try to stop it, okay, and this is what is known as electrical resistance. All the materials have it, okay, all the normal materials have it, and this electrical resistance is a property of the material itself, and it is measured in units called ohm, OHM, ohm. They are named after German physicist George Simon Ohm, who was a teacher, and of course he did a very important thing. He invented what we call the Ohm's law, and this is of course the Ohm's law written right here. What does it tell us? What does the Ohm's law tell us? Okay, like look at the picture right here and you will probably get an understanding. The volt or the potential difference across the circuit is trying to drive the current. This is what this picture is telling you. And the resistance inside the circuit is trying to stop it. And this is what this equation is also telling you. As I increase the voltage, the current increases. As I increase the resistance, the current decreases. Right? Because the resistance is trying to stop the flow and voltage is trying to drive the flow of electrons. And the current is just the flow of electrons. Okay, so this is the current and this is the voltage and this is the resistance. So now with this basic understanding, okay, this equation is very, very important. I is equal to V by R. This Ohm's law is very, very important. And with this equation with us, now we can solve some more interesting, more complicated things. Right? But before we do that, let's look at this one more thing. All the things around us, like I said, have resistance. Some of them have more resistance than the others. Some of them have so much resistance that they don't allow any significant amount of electrical current to pass through them, and they are known as actually insulators. Conductors are of course materials which allow the electrical current to pass through them, and one example of a conductor is this copper wire which has been used right here, okay, and it's there in all of your electrical wiring at your home and things like that also. The copper wire is, and all other metals, they are generally all very good conductors of electricity. Reason being, they have free electrons. Like the same reason they conduct heat is the reason why they conduct electricity also very easily, the metals, right? I mean, we studied in the chapter with heat that they have free electrons. The electrons are free to go around, and that's why they conduct the electricity very, very easily. As soon as you apply the voltage, the electrons, they are ready, they just take off. Okay, so that's why all the metals are good conductors of electricity. They are good conductors of heat also. They are also good conductors of electricity. One of the things here to note is not all metals are good conductors of electricity. That does not mean that all non-metals are actually insulators. There are some conductors among non-metals as well. For example, our body is a non-metal. We are not made up of metal, but we are good conductors of electricity. Similarly, the lead in your pencil, it's the black color graphite, it's made up of graphite. That is also good conductor of electricity, although it is not a metal. Now with this basic understanding, let's just see how we can put this equation I is equal to V by R, the Ohm's law, okay, very, very important again, to good use, how we can use it. The first thing to understand is when we are doing experiments with electricity, I really encourage you especially to do this experiment where you connect the bulb, at least once, do it, okay, it will be very enlightening, both literally and figuratively. So if you're doing experiments with this electricity, stay away from mains power, okay, the power which comes through the plugs in your house, stay away from that, sincerely, okay, just do that. And the reason being, the mains voltage is actually very, very high. Okay, in India it's 220 volts, which is actually very, very high. Compared to that, a normal dry cell, a normal battery has 1.5 volts. So because the voltage is very high, the current also would be very, very high, because as the voltage increases, the current increases. So if we were to touch the mains switch or the mains plug or the mains line by mistake, we would get a big shock. It could probably be deadly also, because large amount of current would flow through our body. Another thing to note here is, let's say that I took this positive terminal of the battery and I connected it using a copper wire, which is, mind you, a very good conductor of electricity. I directly connected this positive terminal with the negative terminal. What would happen then? Right? I mean, of course, the electrons would start flowing, the current would start flowing, the traditional current would start flowing from the positive side to the negative side. large amount of electrons would start flowing from negative to positive side, because the resistance of this wire is very, very less. So the current would be very, very large. Inside the battery, there are of course chemical reactions going on which are producing these charges, which are doing the charge separation. Because we are moving lot of charges, lot of current through the external wire, the reactions inside the battery would also happen lot faster, and the battery would quickly exhaust. It will also heat up a little and it would quickly exhaust. So we should never connect the battery directly. We should always connect some kind, like a bulb or a resistance, okay, what we call a load, on the other side of the battery. Now, moving on to a little more formal stuff, like little more formal things. We have seen how to connect actually a battery to a bulb. We can replace these battery and the bulb. When we are drawing diagrams on paper, we would replace this battery with a parallel lines, one is small and one large. Okay, this is the symbol of a battery in an electrical circuit. The bulb is represented by these curly lines enclosed inside a circle. And of course, our switch, which is also very, like we said, very important part of our circuit, is represented by a bar, just a bar across two terminals. If the bar is such that the two terminals, it is touching both the terminals, then the switch is closed, the current can flow. If the bar is touching only one of the terminals, then the switch is open and the current would not flow. Very, very simple. Now, imagine what would happen if I were to, instead of having just one battery, I had two batteries in a circuit. So previously I had only just one battery and the bulb was glowing. Now instead of one battery, I added another similar battery to the circuit, such that their EMFs were added, their voltage across them got added, their work done would be added. The way to connect the battery in such a way would be to connect the plus of one battery, the anode of one battery, to the cathode of the other battery. So if I were to do this, the voltage in the circuit would increase and correspondingly the current would also increase. As the current increases, the heat generated by the lamp would also increase. Remember, like the current flowing and the lamp providing the resistance, like now larger the amount of current, the more the heat would be, the more the sort of the more electrons would hit here and there, and the more heat would be generated inside the lamp. So the more heat is generated, which means that the lamp would grow brighter. Okay, so that is what would happen. If we continue to increase the voltage, right? I added one battery, I added one more. If I continue to do this, then at some point, such a large amount of current would flow through the lamp that due to the heat generated, the tungsten, the filament of the lamp would burn out completely. Okay, and we say that the lamp would then just fuse. Now, let's take the other scenario. Let's say what happens if the battery remains the same, and instead of having two lamps, instead of having just one lamp, I connect another lamp to my circuit. Now the same voltage remains the same in the circuit, but now the resistance has actually doubled. Instead of just having one lamp, I now had two lamps. So of course the current would reduce. Due to this reduced current, the temperature inside the lamp would reduce, and of course the lamp would become dim. So each individual lamp would now be lit dimmer. Now, one of the very common examples, and this is actually given in your book also, of a circuit is a torch. It is most commonly used. Like we said, these two electrical cells inside this torch in this diagram are connected in series. So they are connected one after the other, and their respective potentials are getting added. So if one is 1.5 volt, one is 1.5 volts, I have a total of 3.0 volts available across their terminals, right? Across their essentially combined terminals. Now let's try to see how the electricity would flow inside this torch, right, when it is on. So of course, the electricity, or the traditional electric current, or just the current, would start flowing from the anode. Then it would go inside the filament. It would come on the other side and then travel the wires. Finally, it reaches the bulge of the switch, this inverted V, it travels a little bit through the switch, and from the other inverted V, it can now go up to the other metal plate and then finally reach the cathode. Of course, the EMF inside the battery, the chemical reactions are further driving these electrons or this electric current, sorry, not the electrons, the electric current across to the back to the anode. Now, this is what happens when the switch is actually closed. When the switch of this battery is open, when we shift it, let's say downwards, then these two V's would come here. And if you notice, they are no longer making contact with the metal plate above. Circuit is therefore broken and the torch becomes off. Right? Nothing magical about it. It is actually pretty simple if you think about it.